All right. Hello, everybody again. Uh, so in this video, we're going to start covering the very first chapter of the course, which should hopefully be review. It's just going back over some of the basic chemistry that applies to all of biology and will be important for understanding the anatomy and physiology content of this course. So let's talk about chemistry. The major concepts from this chapter that we'll be focusing on is the general structure of the atom, chemical bonds and how they work, and then essentially how they apply to water, because water is the basis of all life, and the polarity of water is what gives it all of its properties and thus dictates basically how everything works in living systems. So very important to understand the function of water and the chemical structure of water. We'll look at molecule formation. We'll talk about pH and buffers, and then all the various biomolecules and some of their applications. The application stuff we will build on in the next chapter, and obviously touch back on throughout this entire course. But we'll take a quick look at some of the major applications where they show up in the body in this chapter. So this first video is going to go through structure of atom up to the end of water, or I guess probably all the way through buffers, and then I'll do a separate video focusing on the biomolecules, so splitting this up into two. So starting with the structure of the atom. Atoms make up all matter. So everything that takes up space in this universe is made up of atoms of some type. Okay? So matter, like I just said, is anything that takes up space. In this three-dimensional universe, we have space, which is empty, and then the things that fill up that space, which is matter. Mass, no matter what measurement you're using to determine that mass, whether it's weight or volume, right? Mass is just a measure of the amount of matter that some object contains. And all matter is composed of elements. All elements are made up of atoms. So an atom is just a single unit of any element. And an element is referring to those specific named things like hydrogen, oxygen, carbon, nitrogen, helium, right? Those are all elements that have known properties to them. And one single unit of a carbon is one single atom, right? So multiple atoms of carbon can come together to make bonds to form a molecule. Multiple elements can bond together can bond their atoms together to make molecules, right? An atom is just that one single unit, which we typically depict looking something like this, right? The bonds being shown there. And so all of the known elements or the defined elements of our universe have been organized into what we call the periodic table of elements. Okay. So there are around 118 defined elements. Many of those are artificial or have been created in a lab. Only 92 are those that occur naturally, at least from what we have observed and defined. And then from that list, less than 30 of them can be found in living things, at least commonly found in living things. And so we'll talk about the major elements, or I have a list to show you very soon. But most biological molecules, most of our organic molecules are going to be composed mainly of carbon, oxygen, and hydrogen. And then a lot of the other elements like nitrogen and fluorine, phosphorus are going to be acting as functional groups to give those molecules some sort of function. And then other elements like chlorine, sodium, magnesium, manganese, etc., are acting as minerals, which help with things like cell signal transduction and the process of diffusion and energy, etc. So these are all of our known elements. Each element is strictly defined by the number of protons that that atom has. So any element with one single proton would be called a hydrogen. That gives it its atomic number. Any element with 8 protons is an oxygen. It doesn't matter how many neutrons or electrons that element has. If it has 8 protons in its nucleus, that is an oxygen. That is what these numbers and names mean, referring to the number of protons. And there's other information we can gain from that, which we'll touch back on in a second. But here are our principal elements of living things. Like I said, most of our organic molecules going to be mainly composed of oxygen, carbon, and hydrogen, with a big emphasis on carbon as the backbone for all organic molecules. Some of our major minerals that we'll talk a lot about are calcium, potassium, chlorine, and sodium, and we'll touch on their major functions in lots of places throughout this course for the role that they play. And so a majority of the time that we're referring to these elements, it's going to be based on their element name from the periodic table, right? So if you see an H, it's referring to hydrogen, an O, it's referring to oxygen, right? I just realized this table has oxygen as OXI there for some reason. This is from the text, so that's disappointing. Chlorine will be Cl, potassium will be K, right? So becoming familiar with what these symbols mean is going to be helpful. When they're being written out as a molecule or in a chemical formula, a number before that element is referring to how many individual atoms of it. So these are 2 atoms of hydrogen. A number as a subscript is referring to how many atoms of that element are bonded in a molecule. So 2H would be 2 separate hydrogens. They are not bonded to each other. 2O would be 2 separate oxygens. They are not sharing a bond. But if you see a subscript and a connected thing, those are all bonded. So H2 are 2 hydrogen atoms bonded into one molecule. H2O is 2 hydrogens and 1 oxygen bonded into one single molecule of water. So hopefully you're already familiar with that, but that is going to be important, going to show up a lot in this course and throughout biology and chemistry. So now going back to atoms themselves, now that we're familiar with some of the basic information about how we talk about them, where we get this info from, all atoms share the same basic structure. Atoms are made up of 3 different types of subatomic particles. We have protons, neutrons, and electrons. Each of them have their own specific properties and will always show up in the same basic locations. So the very center of an atom we call the nucleus. Just like how we have a nucleus in our cells, which houses our DNA, the nucleus of an atom houses the protons and the neutrons. These are the only 2 subatomic particles that carry a significant mass, right? So if you, that famous gold foil experiment where atoms were shot at a thin sheet of gold, some atoms were able to fly through that because their nuclei were not hitting each other, and some atoms were bouncing off because their nuclei were hitting the other nuclei. Right? So there are parts of an atom that do not have a significant mass that we refer to as the electron cloud. That is outside of the nucleus, and that is where the electrons exist. So electrons have a negligible mass or a hard to quantify mass. They don't really seem to bounce off of things or hit things. They move and function a lot more like photons. Right? It's a high energy particle that doesn't really carry mass. But our neutrons and protons do have mass. Beyond that, some of our particles are going to carry a specific charge. So protons carry 1 positive charge each, and electrons carry 1 negative charge each. So in this element, this would be the atomic number 2. So if we go back to our periodic table of elements, since we had 2 protons, we know we're looking at a helium here. It has 2 protons, giving it 2 positive charges, and it has 2 electrons, giving it 2 negative charges. So those would cancel out, and the net charge of this atom, of this element, would be 0, because 2 positives cancel out with the 2 negatives. Neutrons, although they carry mass, do not contribute to the charge of an atom. So you can see that depicted a different way here, and then here is all that info basically broken down for you. So our protons and neutrons exist in the nucleus. They each carry a mass or contribute 1 to the total mass of that element, but only protons have a charge in that nucleus. They carry a positive charge. Outside of the nucleus, we have electrons, which exist in the electron cloud. They each carry a charge of -1, but do not contribute to the mass of the element. And so all of this information, how many protons, neutrons, and electrons would exist in the most common form of each element, that information can all be read from what is available on the periodic table. And so being able to interpret that information is quite important when trying to determine other things like how many valence electrons that element has, and thus how many bonds it can make and what types of bonds it would make, etc. So in the periodic table, we have three key pieces of information. We have the chemical symbol, which for oxygen, the chemical symbol here is O. We have the atomic number, which is typically in the top or the top left. That tells you how many protons that element has. So oxygen is defined by having 8 protons in one atom of that element. And in the most common version or most common form of this element, it would be stable or neutral, meaning it would not be carrying a charge. And so if it's not carrying a charge, then we can assume that this element is going to have the same number of electrons as it does protons. So if we see that oxygen has the atomic number 8, we know right away that means oxygen has 8 protons. We can then also assume, since it's going to be stable in its most common form, that it also has 8 electrons, canceling out and giving it a neutral charge, a net charge of 0. So the atomic number tells you the number of protons and number of electrons for most elements, or at least most commonly for that element. Our third important piece of information is the atomic mass. This is always at the bottom. So for oxygen, we have a pretty nice atomic mass. It's atomic mass of 16. And this number is telling you the number of protons plus the number of neutrons. Right? Only protons and neutrons contribute to the mass of an atom. Electrons do not. So we know that oxygen carries a mass of 16 in its most common form, and we know that from its atomic number, it has 8 protons. We can also use that to determine how many neutrons. So in this case, 16 minus 8 would tell us there are also 8 neutrons in the nucleus of this atom. And so it'd be a good idea to practice this. So if you would like to pause the video here and practice determining all of the subatomic particles from iodine with this information, please give it a pause. And we'll talk about that in a second. Okay. So from this, the easiest piece of information to gather are the number of protons and number of electrons. Right? The atomic number tells you how many protons that element has. So iodine has 53 protons. Done. In its most common form, it will be stable or neutral. It'll have a net charge of 0. So if it has 53 protons, which carry a positive charge, we can also assume it will have 53 electrons carrying a negative charge, thus canceling each other out. So iodine should have 53 protons and 53 electrons in its most common form. Our last piece of information to determine is its atomic or its number of neutrons. And we will do that through the atomic mass. So again, only protons and neutrons contribute to atomic mass. So our mass is 127. We know that iodine has 53 protons, so we can subtract 53 from 127, and that'll give us 74. Yeah, that'll give us 74. And so we know that iodine has 74 neutrons in its most common state. And so using this information, we can gather all of that. We can then expand on that with knowing where those electrons exist in the electron cloud, which we're going to talk about here in a second, which becomes really important for how they bond. We know that if it has a different number of neutrons, that would be an isotope. If it has a different number of electrons, then it typically should, that would make it an ion. So we can expand on that info in a lot of ways. And so one of the most important expansions or applications of this knowledge is determining the location of our electrons. So electrons in the electron cloud will exist at different energy levels that we refer to as shells. And so each energy level has a different number of electrons that it has the ability to hold. And on average, that ends up being following these general rules. So the first shell, the closest energy level to the nucleus, can only hold a maximum of 2 electrons. So if that element is holding more than 2, the rest of those electrons are going to be placed on the second shell, which is outside of that first shell, farther away from the nucleus. The second shell can hold up to 8. So if we have more than 10 electrons, because the first 2 would go in the first shell, and then 8 would go in the second. So if we have more than 10 electrons in this element, they are going to move to the third shell, and so on and so forth. Right? And the third shell can similarly hold a maximum of 8. And this is not a law. These are not steadfast rules. These numbers can vary. But on average, and in 99% of examples of looking at elements, the electrons will follow these rules and exist at these different energy levels. And we care about this because however many electrons are on the outermost shell, what we call the valence shell. Is that my next slide? I guess not. However many electrons are on that valence shell, those are our valence electrons. And again, valence is referring to the outermost. Those are the electrons that can be used to form bonds. So that is our next thing to talk about. So again, that outermost shell is referred to as the valence shell. And elements tend to have a natural drive to fill their valence shells with whatever method is necessary to do that. And there are two main methods for achieving this goal. And by doing that, they are going to form bonds. So bonds can be formed by either sharing or exchanging valence electrons between two or more atoms. So if atoms are going to share their valence electrons, or if an atom is going to give away its electron to another atom, that is going to cause a bond to form between them. And like I said, there's two main ways to do that. So here's a depiction of generally the valence electrons for all or a lot of the atoms or elements we're going to be talking about in this class. Carbon is the major backbone for most biological organisms because it has 4 valence electrons, leaving it available for 4 possible bonds. Right? If this shell can hold a maximum of 8, it could share an electron with 4 other atoms, and thus create this great like middle piece. If you were to build something like with Lincoln Logs or Legos, right? Having 4 connections going in every direction, right? Making it the backbone for a lot of larger molecules in living systems. Carbon is also not particularly greedy with its electrons, so it tends to form non-polar covalent bonds, depending on what else is bonded with it. We'll talk more about that later. But all of that comes from carbon having these 4 valence electrons. And so for covalent bonds, or when electrons are being shared, right, their valence shell ends up overlapping like this. So oxygen has 6 valence electrons on its own. You can see that depicted here, 1, 2, 3, 4, 5, 6 around this oxygen. And so when 2 oxygens want to bond, or if they each need to fill their valence shells, they can share 2 valence electrons each. And now each oxygen is satisfied. It has 8 on that second shell, 1, 2, 3, 4, 5, 6, 7, 8, because it is now sharing the 2 that came from the other oxygen. And we can depict this in multiple different ways. So in a molecular formula, it would be notated as O with the subscript 2, because there are 2 oxygens bonded together. You can draw out their electron distribution like this, with the valence shells overlapping. You can use a Lewis dot structure formula, either showing all electrons involved or just using these lines to notate the double bond between these oxygens. And then our space filling model to show 3-dimensionally what that element would look like in space. So water is going to be another common element we talk about. And so in this case, again, oxygen has 6 valence electrons on its own. Each of these hydrogens only has 1. And so it is at its first electron shell. And so it only needs 1 more electron to fill that and be happy and satisfied. And so it will share one of its electrons with one of the free electrons on oxygen. And so if we have 2 hydrogens, we can fully fill oxygen's valence shell, 1, 2, 3, 4, 5, 6, 7, 8. And each of these hydrogens is satisfied because it has 2 electrons in its valence shell. Again, this is the first electron shell, so it can only hold 2. So 1, 2, 1, 2, right? And now all the elements involved are happy. But something we're going to talk about more here in a second is that oxygen is extremely electronegative, meaning that it has a very strong pull on electrons. It's really greedy with its electrons. And so even though we're sharing electrons here between all the elements involved, oxygen is actually going to pull those electrons much closer to itself and away from hydrogen, which is going to end up giving this molecule slight charges on its different sides, making it a polar molecule. I'll touch back on that in a second. So here we go. So when elements are sharing their electrons, their valence electrons, that is referred to as a covalent bond. We have 2 main types of covalent bonds. So again, covalent is defined by the sharing of valence electrons. But a covalent bond can either be polar or non-polar, depending on how those electrons are being shared. So like I said, oxygen is really greedy with electrons. It's very electronegative. And so especially when it's bonded to a very small and weak element like hydrogen, it is going to pull those electrons closer to its nucleus and thus the electrons are going to be pulled away from the nucleus of these hydrogens. And electrons carry a negative charge, right? So if the electrons are spending more time near this oxygen and farther away from those hydrogens, this oxygen is going to end up with a slightly negative charge, a partial charge, which is notated with that Greek gamma, I believe, the lowercase gamma here, with that negative to show that oxygen has a partial negative charge. And thus these hydrogens are only left with the protons in their nucleus, and so they will end up with a slightly positive charge. And that makes this molecule a polar molecule. We have two different poles, just like how our planet has a north and a south pole. This molecule has a negative pole and a positive pole, right? Clearly different sides of the molecule, which are going to interact with the environment in different ways, right? Because now we have a negative charge, which is going to create a magnetic attraction with any positively charged things near it. And each of these hydrogens now has a positive charge, which is going to create a magnetic interaction or attraction with any negatively charged things near it. And so again, this is just one example of a polar covalent bond. This is going to be the most common example that we talk about, as it plays a big role in how water functions, and thus a big role in how life functions. But polar covalent bonds are when electrons are not shared equally. There's an unequal distribution of the electrons that are being shared. A non-polar covalent bond is just the simple electrons are being shared, they're evenly distributed, there is no partial charge. Like I said, carbon tends to make these non-polar covalent bonds unless it is bonding with an electronegative element like oxygen or nitrogen. So CH4 here, methane, carbon with 4 hydrogens bonded to it, this would be non-polar, there's no charges, thus no magnetic attractions to other charged things. So now we're going to dive deeper into water, expanding on this polar covalent bonding, the polarity of water, and why that matters. So covalent bonds are considered atomic bonds. They are formed between different atoms. But because of that polarity, they can start forming molecular bonds. So attractions or bonds between different molecules. So since water is polar, giving it some positively charged ends and a negatively charged end, it is going to form those magnetic attractions with any opposite charges nearby. And with water specifically, we refer to those attractions as hydrogen bonds. So in this water molecule, you can see that one of the hydrogens, which is carrying a slightly positive charge, is going to form an attraction with a nearby partially negative nitrogen. Nitrogen is also electronegative, so when it is bonding with hydrogen, it becomes polar. And so they now have an attraction between them, right? That magnetic attraction, that magnetic pull, that idea of opposites attract is essentially a law throughout all of chemistry. Positive and negative charges attract each other and will form some sort of attraction and interaction that we can refer to as a molecular bond, in this case, a hydrogen bond. And water is doing this all the time with other water molecules, which gives it a lot of its properties. You can see we have 5 water molecules here, each of them involved with a hydrogen bond on this one central water molecule. So we see that depicted again here. Right? All these dotted lines are showing those magnetic attractions that are going to hold these water molecules to each other. And water can very easily and quickly break and then remake these bonds. So not only does it have an attraction to all the water nearby it, but it is very quick and easy to break and rebuild them, which does a lot to the energy of a system, which we'll expand on more. And so a lot of the applications of this hydrogen bonding are explained more in depth in these next few slides. So how that plays a role in cohesion and surface tension, adhesion, why ice floats and why that's important. Right? Water's high specific heat capacity, so how it manipulates the temperature of an environment based on the use of energy to break and remake hydrogen bonds. Why living nearer to a large body of water is typically more temperate and more of a controlled climate, whereas living farther away has a more volatile climate. I'm not going to spend time diving into those because they're not all relevant to what we're talking about in anatomy and physiology, but they are discussed briefly in the textbook, and I have slides on them here if you want to learn more about those applications of water. please feel free to ask me. But I'm going to focus on the content that applies to what we talk about in this class. So the major part of how water is going to be involved here is the way it dictates how cellular environments and molecules in those cellular environments are going to function. So because water is so common, not only on this planet, taking up 66% of its mass, but also in our bodies, taking up 70% of our mass, right? Because all of your cells are filled with water, a majority of the spaces in your body are filled with water. So the things that water can and cannot interact with are going to dictate how those things travel in those environments and how they can be used. So water is polar, meaning anything that is charged is going to form a hydrogen bond with water or when exposed to water. Things that do not carry a charge are not going to interact with or bond with water. And so we refer to different molecules, different types of molecules as either hydrophilic or hydrophobic based on their ability to interact with water. Hydro is a prefix referring to water. Phile is a suffix meaning the love of, so these are water-loving substances. Phobe is a suffix meaning a fear of, so these are water-fearing substances. And these terms generally just refer to can it bond with water or not. So a hydrophilic substance is any molecule that can bond with water. So these are going to be polar molecules, these are going to be ions, right? Anything carrying a charge is going to form an attraction with water. Hydrophobic substances are those that cannot interact with or bond with water. And so this is anything that is not carrying a charge. Right? And so not only can they not interact with water, but they tend to be essentially repelled by water. Nonpolar substances don't form bonds and they tend to push away from it. So for instance, the fatty molecules, these phospholipids that exist in all of the membranes of cells, have both a hydrophilic and a hydrophobic component. Because as I just mentioned earlier, the inside of cells are mainly composed of water, and most of the external environments of our cells are going to be water-based. And so these phospholipids that make up our membranes have hydrophilic heads that can point towards the water and interact with it on both sides, and then hydrophobic tails that point inwards away from the water that prevents just the free diffusion of a lot of molecules and create this selectively permeable barrier, right? We have an internal portion of this wall that cannot have water freely move through it, or at least not in large quantities. And then we have a hydrophilic head that can interact with and bond with water and thus maintain its structure. And so we'll talk a lot more about phospholipid and membrane structure in the next chapter. Okay? But because it has a hydrophilic and a hydrophobic portion, phospholipids are referred to as amphipathic. Right? So that's another terminology. A molecule that has both hydrophobic and hydrophilic regions to it are amphipathic. Like amphibians, which can live in the water and on land, right? They have the best of both worlds. Phospholipids are amphipathic because they can bond with water on some of their parts and they cannot on others. Like I said, we'll expand on plasma membranes and cell membranes in general a lot more in the next chapter, but that is a big deal with how things work. So our second type of atomic bonds, we talked about covalent bonds and how they can either be polar or nonpolar, and those are bonds between atoms. Our second type of atomic bond are ionic bonds. So whereas with covalent bonds, those bonds were made through sharing electrons, ionic bonds are formed when there is an exchange of electrons. So in this case, we're looking at a salt, and all salts basically form their bonds this way, of sodium and chlorine. Sodium is the atomic number 11, so it has one valence electron. In order for sodium to fill its valence shell, that would technically be impossible. Right? It only has one electron to offer as a share, so it could get maybe one more electron, but it would never be able to fill its shell by trying to share with just this one. So instead, sodium can give up this electron to some other element like chlorine, and that would then remove that valence shell and move down to the second valence shell, and now it has a full shell. So instead of trying to share and fill up the outermost shell that it already has, it can give away this electron and move down to that lower energy level, and now it feels stable and happy. And so larger elements like chlorine, which have 7 valence electrons, are very happy to take that electron, fill its outermost shell. Now it's happy without needing to share. It just gained a whole new one. But remember that electrons carry a charge. They have a negative charge. And so if we're completely removing an electron from one element and adding it to a new one, that is going to change the net charge of each of these atoms. So sodium is losing 1 electron. So it is now going to carry a +1 charge. It now has 1 more proton in its nucleus than it has electrons in its cloud. So it'll have 11 protons and 10 electrons. So that'll leave it with a +1 charge, making it an ion, a cation. I think it's actually, yeah, I expand on that here. Right, so it's lost an electron and now has 1 more proton than it does electrons, so it has a +1 charge. Ions are any element carrying a charge, any atom carrying a charge, and a positively charged ion is a cation. So you can think of that T as a plus. Cations have a positive charge. This chlorine, which has just gained an electron, now has 1 more electron than proton, and so it is carrying a negative charge, and we refer to those as anions. So if you can remember that cations with the T as a plus are positively charged ions, then this other term, anion, is negative. But we have not formed a bond yet. This is simply the first part of how ionic bonds form. We get an exchange of electrons. The bond comes from these opposite charges, right? The opposites attract. That is true throughout chemistry. So now that we have a cation and an anion in close proximity to each other, they are going to form a magnetic attraction to each other, and that is the ionic bond. Okay? So we had an exchange of electrons. We now form 2 different ions, and those ions have formed an ionic compound, bonding to each other through that magnetic attraction. And these tend to form much larger structures called salts, or crystals, sorry, of salts, that end up giving that very geometric looking shape. And these are just a bunch of cations and anions that are all forming these magnetic attractions to each other, forming that salt. And sodium chloride in particular is a very common salt. This is table salt, right? That salt that you have in your salt shakers at home, or that you, the most common form of salt that is purchased at a grocery store, right? That we add to our food. That is just sodium and chloride ions bonded together into those salt crystals. And so when you pour salt into something that is wet or water-based, those salt crystals seem to start to disappear, okay? That's because these ions are actually being pulled apart from each other based on the polarity of water. We see that depicted here. And because of this property, because water can form interactions with any charged elements that are near it or charged molecules that are near it and tends to pull them apart from each other, water is known as the universal solvent. It can do this to any charged particles, any ions, any polar molecules that has an attraction on them. It may not pull apart polar molecules, but can pull apart pieces of them in lots of cases. But a solvent is any substance that is capable of dissolving another. So if you are mixing something into a liquid, typically that liquid is the solvent, and whatever you're mixing into it is the solute, that is what is being dissolved. And so water is the universal solvent because it can dissolve basically anything with a charge. Okay? Because of its polarity, it can form interactions with negatively charged things with its hydrogens. It can form interactions with positively charged things from its oxygens. And so in the case of ionic compounds, it will pull those apart. So yeah, it's a very common solvent and is going to play a big role in how things move in our systems and in all living systems. Right? Because again, as I mentioned earlier, almost all internal cellular environments are going to be water-based or aqueous. It's a key term here. Aqueous is referring to any solution carrying water. So most or all internal environments of cells are aqueous, and almost all external environments of our cells are going to be aqueous. So understanding how things interact with water ends up playing a big role in how we can use them. And so when water dissolves something or forms these hydrogen bonds, it's going to essentially completely surround that ion or molecule with multiple water molecules. And we refer to that as a hydration sphere. This keeps these ions separate from each other, or prevents other interactions for molecules like glucose, right? Because it now is completely covered by this sphere of water, a hydration sphere. These ions end up playing a huge role in lots of different things later. So having the ability to dissolve these things naturally by just having water in this space allows us to use them as their individual minerals, like calcium playing a big role in muscle contraction, sodium playing a big role in potassium, playing a big role in signal transduction, chlorine playing a big role in neurotransmitter function, right? So being able to dissolve and then have these ions in their individual forms allows us to use them for various functions, which we'll talk a lot about throughout this course. We don't need to really talk much about electrolytes. Electrolytes is essentially referring to any soluble salt, so any inorganic compound that will dissolve in water and thus conduct an electrical signal because they are carrying a charge. Okay? So electrolytes are kind of just another term for salts, because a majority of salts are going to be able to conduct an electrical current. Okay, and I believe our last thing on water here, is their role in biological chemical reactions. So almost all major molecules, or I do think this applies to all of them, all major biological molecules can be formed by removing one water molecule and can be broken apart by adding one water molecule. It's not just as simple as that. There needs to be energy and enzymes and things to play a role. But essentially, when forming a bond between two organic molecules, we are removing a hydroxyl group from one of the molecules and a single hydrogen from the other, which is going to create a bond available on this carbon and on this oxygen. And so we remove those elements, they come together to form water, and now that carbon and this oxygen can create a new bond. That is referred to as dehydration synthesis, removing water, and that creates a bond between two organic molecules, so making a larger molecule, a polymer. And then the opposite is true. When using energy to break apart this bond, we can add water to stabilize the carbon and the oxygen that are losing a bond, right? So we split this water in half, add a hydroxyl group to this carbon, a hydrogen to this oxygen, and then some energy, of course, and an enzyme to help break that bond apart. And that is referred to as hydrolysis. So adding water can break polymers into their individual monomers. So water is a critical component of the chemical reactions of even nonpolar molecules. Okay. And then the last portion of this part of chapter 2 is going to be talking about pH and buffers. So pH is a scale referring to the acidity or the basicness of a solution. And so pH is determined by the negative log of the concentration of protons, these positively charged hydrogens, these hydrogen cations. Hydrogen is one single proton with one single electron. So if you see hydrogen notated like this, H+, a hydrogen cation, that means it does not have an electron. It is a proton on its own. If you see hydrogen notated as H-, that is a single electron on its own. So just keep that in mind. So this, what is being shown here, these brackets referring to concentration, this is the concentration of protons in the solution. And so essentially, on this pH scale of 0 to 14, the lower the number is referring to a more acidic solution. And that is also referring to a higher number of protons. I don't know why they did it this way with this calculation. I don't fully understand the math on this and the relativity of why it was done. But the more protons, the higher concentration of protons, the lower this pH value ends up being. So a pH of 0 is an extremely acidic solution that is an extremely high concentration of protons. On the opposite end, a pH of 14 has an extremely low concentration of protons and may have a really high concentration of these hydroxides, of OH negatives. So essentially, at its most basic level, an acid is any solution that has or is able to give up protons easily, and a base is any solution that is able to absorb protons. And so you could think of this as the two different sides of water. Right? Water could be split into a proton and the leftover negatively charged hydroxyl group. And so water can do both things. It can make a solution more acidic, or it could make a solution more basic, and thus water acts as what we call a buffer. Sorry, skipping ahead a little bit. A buffer is any compound that stabilizes the pH of a solution. This could be done by either removing free protons, so acting as a base and removing protons from solution, or by giving away free protons, acting as an acid and giving up some protons. So a buffer is going to bring that pH number closer to 7. And water is a great buffer because it can do both. Okay, and this was just showing some common solutions and where they fall on this pH scale. So the hydrochloric acid in your stomach is extremely, extremely acidic, which is why it needs to be buffered immediately when it moves into your small intestine by your bicarbonate from your pancreas. Okay. Household ammonia and oven cleaner bleach tends to be really, really basic. So it will take away free protons from whatever solution or space it's being added to. And that's where I'm going to stop for this first video in chapter 2. So in the next one, I will pick up talking about biomolecules, and we can run through the rest of this chapter 2 content. So see you in the next one.